In this video, we'll take a look at a couple examples that relate to our previously discussed topic, right? And those topics involved the law of total probability and Bayes' theorem. So let's take a look at this question. There are two parts to it. I have the stem of the question and the first part of the question already up, right? So let's see. Customers, they can make a purchase of a car that has an engine in any of three sizes. So of all the cars sold, 45% have small engines, 35 have a medium sized, and then 20 have the largest sized engine. And then of the engines with the small size, 10% of them will fail an emissions test within 2 years of purchase, while 12% of the medium will fail within 2 years, and then 15% of the large will fail. So the question is, the first question is, if we randomly choose one of these cars, what is the probability that it will fail an emissions test within 2 years, right? So there's a lot to unpack here. And the first thing I want to highlight is this. And this is one of the things you want to do in all of these questions is identify the partition, right? So identify those sets, right, that never overlap and they capture all of the possibilities, right? And the first sentence is saying that there are only three sizes possible, and then the second sentence goes on to break down the percentage, right? So let's define some sets, and what I'll do is I'll use the same notation that we did for our partition with the a sub 1, a sub 2. So I'm going to say let a sub 1 represent those cars with the small engine, and then a sub 2 will represent those cars with the medium engine, and then a sub 3 will represent those cars with the large engine. Right, and then now let's write down the probability. So the probability that any one of these cars will have a small engine, well, that's given in the problem. That's the 45%, and we can actually write it as a decimal. So I'll go ahead and convert it to 0.45. The probability of the car having a medium engine, well, that's the 35%. So 0.35. And then the probability of the car having a large engine, that is 20%, or 0.2, right? And these probabilities, right, for your partition, they all have to add up to 1, because remember, the partition are the pieces that fit together to make up the sample space. And we know that the probability of the sample space is 1. Right? So these probabilities have to sum up to 1, and if you do a quick check, 0.45 plus 0.35, that's 0.8, plus a 0.2, that gives us 1.0, right? So we have that part. Now let's see what other information is given. It says, if you know that a car has a small engine, it is going to fail the emissions test 10% of the time. If it has a medium size engine, then it's going to fail that emissions test 12% of the time. If it has a large engine, then it's going to fail that emissions test 15% of the time. So those are all conditional probabilities. And what we need is we need another event, right? So this, again, is our partition. Now I'm going to define B. And I don't have to use these letters. I'm just using these letters because they're consistent with what we just developed in the previous video, right? But in general, you can label them any way you want as long as you're clear as to what the information represents. So if we let B be the event that a car fails the test, right? So fails the emissions test, never a good thing, right? Then what we can say is, let's write these down. So let's start with the small. So given a small engine car, the probability that it will fail the test, that's the 10%. So again, I'll write that as a decimal, 0.1. The probability that the car will fail the test given that it has a medium engine, that is 0.12, right? 12%. And then finally, the probability that the car will fail the test given that it has a large engine, that's probability 0.15. Now, these conditional probabilities, they don't have to add up to 1, right? Because these are not all the possibilities. It's just saying if you have a car with a small engine, the probability that it will fail the emissions test is 0.1. But it could also not fail, right? So there are other things not necessarily represented here. So these conditional probabilities, they don't have to add up to 1. In fact, if they're small, like these probabilities, they won't add up to 1. If they're larger, they could add up to something greater than 1, right? It's the partition's probability, right, that has the sum to 1. All right. Okay, so that's all given. So this is what we've done to convert that paragraph into probabilities and conditional probabilities. Now let's see what part A1 says. It says, what is the probability that a randomly chosen car will fail an emissions test, right? So much like that example that we did previously with the urn and the red and blue chips where you had the 2 levels of randomness, it's the same thing here. One level of randomness is you don't know what type of engine the car will have. If you're going to choose a random, right, you walk onto this lot or production facility and you just pick one, you don't know in particular if it has a small, medium, or large. So that's one level of randomness. The other level is it going to pass or fail the test, right? So in order to find the probability that the car will fail the emissions test within 2 years, we use the law of total probability. And as a reminder, this is how it's stated. Now in this case, we have 3 sets that make up the partition, A1 through A3. So the law of total probability says, take the sum as k goes from 1 to 3 of your probability of B given your A sub k times the probability of A sub k, right? So writing that out, this is what it looks like. It's the probability of B given A1, right? So the probability that it will fail given that it's a small car times the likelihood of choosing a small car plus the probability of failure given a medium-sized car engine, that is, times the probability that you'll pick one of those, and then finally the probability of failure given a large engine times the probability of picking that large engine, right? And all 6 numbers that we need are given, right? So the probability of B given A1, that's 0.1. And the probability of A1, that's 0.45. Probability of B given A2, that's 0.12. And then times the probability of A2, that's 0.35. And then finally, the last term, the probability of B given A3, that's that 15% failure rate for the large engines. And then the probability of getting a car with a large engine, that is your 0.2 or 20%. So like that, right? And if you go through and compute this, you'll get 0.117 exactly. So the decimal is exact, or if you wanted to write it as a fraction, it'll be 117 over 1,000, right? So it's roughly, now as a percent, it would be 11.7%. So it's not a high percentage, and in fact, you would want this to be low. If you're the car manufacturer here, you want this percentage to be low. Now, you might say 11.7% is not low enough, and then you go back to the design team and say, how can we improve this by making it lower, right? But that's the probability of just randomly choosing a car and then having it fail the emissions test within 2 years, all right? Okay, so now let's look at another question. And this one is, okay, a record for a failed emissions test is chosen at random. So in other words, we know that failure has occurred in terms of the emissions test. Now the question is, what is the probability that it is for a car with a small engine, right? So what is the probability that, given that we have a failed emissions test, now the car is one that has a small engine? So let's write that up in terms of symbols, right? And this is where we will use Bayes' theorem. So we're asking the probability of it being a car with a small engine given failure. And so again, let me write it out symbolically what Bayes' theorem says. It says, well, you can express this as the probability of B given A1 times the probability of A1, right? So essentially what you end up doing is like flipping the roles of what event has occurred here and which event's probability you're trying to find. So this is the numerator in Bayes' theorem, and then the denominator is what we found in part A. It's all of this, right? In fact, what I will do, I'll just write it with the sigma notation, right, like that, and then we have the probability of B given A sub k times the probability of A sub k, right? So we don't need to rewrite this expression. We have it right there. That's going to be the denominator. This is the probability of failure within 2 years. So what's on the top now is just this part. So basically, what Bayes is saying, if you're trying to figure out what is the likelihood that it came from a particular part of the partition, take that term, right, that corresponds to that part of the partition, out of the entire sum, make that your numerator, and then make the entire sum your denominator, right? So it's like what percentage of all the failures, right, can be attributed to cars with small engines. So that's basically what it is. I mean, it's a fancy proportion. That's what it boils down to. All right. So let's go ahead and well, we know what this is. That this is the 0.1 times the 0.45, and that's in the numerator. Again, I don't have to write out all these terms because we've already computed it. So basically what I'm taking now is, so in fact, let me do it like this. So that is the numerator there. And then all of this is the denominator. So put the red over the green and you've answered the question. So we have our 0.117. Now it turns out that this whole thing simplifies to 5/13. And as a decimal, now it's not a decimal, you have a prime number here in the denominator, so you're not going to get a nice terminating decimal, at least not this one with 13, and you'll end up with 0.3846 if you round to 4 decimal places. So that's really just an approximation. So it's roughly 38%. So there's a 38% chance that if the car fails that emissions test within 2 years, then it would have had a small engine, right? And we can do this for all other engine types, and then it gives you this idea to say, okay, yeah, of the ones that fail, you know, the A1 is the highest likelihood, or A2, and so forth, right? So that's Bayes' theorem. What I want to do is show you. So the way we did A and B, it was purely based on the formulas, right? And the formulas are helpful. They're very useful. But let's say you'd want like a picture or something that you can look at that can help you answer the same question. So what I've done, I've copied the question again. Here it is. And I'm going to show you how we can set up this in the form of what we're going to call a tree diagram. And many of you, you've seen tree diagrams before. And it turns out they're very, very useful in questions like this. So I'm going to set up my tree vertically. So it's going to start up here. And the first set of branches will represent the partition, right? So that's those are the sets that break up our sample space in that mutually exclusive, exhaustive ways, right? It covers everything and they don't overlap. So in this case, we need 3 branches because we have 3 engine types, right? So I'm going to have it here. Maybe one in the middle, and maybe one there, right? So, and I'll use the same A1, A2, actually, let me put this there since I'm going to draw branches down from these in a second, and then A3, all right? Yeah, let me go ahead and take this one off as well. So here we got A1, all right? And what we can do is we can actually label this branch with its probability. So the probability that a car has a small engine, that's the 45%. So you can actually put that probability on that branch. And then there's a 35% chance of getting one with a medium size. So put your 0.35 there. And then your large engine, there were 20% there, so put your 0.2 there, right? So that's the first layer of randomness. Now the next layer now is a given car, are they going to fail the emissions test or not? So for instance, it's either, so I used B, so it's either B or not B. So the car is either going to fail or not fail. And that's true for all engine types. So there and there. Again, well, actually now I can put these below because we don't have any more branches. But again, if you have a complex enough experiment or scenario, then yeah, you could have this tree be very branchy, lots of leaves, but there we go. So fail, not fail. And then now we can label the green branches with the necessary percentages. So small engine vehicles, they fail at a 10% rate. So 0.1. So the complement of that would go on this branch, and that's your 0.9. Same thing for A2. They have a failure rate as far as the test is concerned of 12%. So 0.12. And then the complement of that, so they're going to pass the test or not fail with a rate of 0.88. And then finally, large engines, they have a failure rate of 0.15 and therefore a not failure rate of 0.85. All right. So right away, do you see how much information this tree holds? I mean, we didn't need the not failure rates, but it's all captured there, right? So for instance, how could we use this to answer the question about like part A? So now we're redoing part A. Maybe I'll just switch back to black, right? So we're redoing part A, and part A says, what is the probability that a randomly chosen car will fail the test within 2 years? Well, failure can happen in one of 3 ways. Here, here, and here, right? So if this is our starting point, right? First we have the different types of cars, and then we have the failure rate of each type of car or car engine. In order to figure out the probability of B, right, which is what we want, so the probability of B, look at all the ways you can start from the top of your tree and get to a branch that's labeled with B. So there are 3 paths you can take here, right? There are 3 paths you can take. You could go along basically there, or there, or there, right? So you can take those 3 paths. Now, when you do this, what you are doing, for instance, is saying that this would be the probability of A1, and then this right here is the probability of B, of failure, given that you've taken this branch, right? So it's all there. All the pieces of the law of total probability are there, but what makes this a little bit easier to understand is that it's visual. So the way you can say it is, there are 3 ways I can end in a B. The first way is by going along this branch and along this branch. And every time there's an and, you multiply. So it's 0.45 times 0.1, right? Or another path would be like down the middle. And anytime there's an or, the operation is addition, right? So it's like another way of getting to this particular end result, which for what we're looking for is failure, right? Not necessarily a good thing, but that's the event whose likelihood we're measuring. So now going down the middle, that path is again now moving along the A2 branch and the B branch that emanates from A2. So given A2, the probability of failure, that's 0.12, so we multiply these two, right? Moving from one branch to another is times, and then moving to a completely different path, that's plus, right? So we have plus, so it's or, so just keep, yeah, if you just keep using those analogies, and is times, or is plus, right? And then the last path is your 0.2, and then times the 0.15, right? And that expression is what we got earlier. That's equal to the 0.117. Now, let's say we wanted to answer part B, right? So notice the what we've written down, it's not so complicated, and it's still helpful to keep, to have your events labeled so you can keep track of, when something happens or when it doesn't happen, and all the necessary probabilities. But now remember what part B asked us. It says, what is the probability that it's a small engine car given that it fails? Well, this is it's a conditional probability. So even if you want to forego the formality of Bayes' theorem, simply use the definition of a conditional probability, which is the probability of A1 and B divided by the probability of B, right? This is completely correct. It's just that what Bayes does is Bayes breaks it down even further and then expresses this as a conditional probability, and then the bottom using our law of total probability. But we don't necessarily need to do that because all the information that we need is already there in the tree. So for instance, that A1 and B, that's this branch right here, right? Yeah, it's both of these together. So it's that probability, again, with the and, it's your 0.5 times 0.1. And we don't even have to rewrite the entire expression. We know what the probability of failure is. It's this, 0.117. So 0.117, and that's what comes out to the 5/13ths, right? So this is an alternative way where you still have to use at least the definition of conditional probability here, right? But as far as just the eyesore of Bayes, not that I find it to be an eyesore, I think it's a beautiful theorem. But again, from a practical standpoint, just wanting to problem solve, I think having a tree in front of you and knowing how to, when you go like along several branches as a product, or when you take an alternative path overall, would be a sum. Just to show you, how this can be utilized some more. Now, what if the question was about not failing the test? Right? So let's do another example that wasn't on our first page, and then this will be our last example. But let's say we wanted the probability, given that it did not fail, what's the probability that it's a medium-sized car, right? So what if we want the probability that it's a medium-sized given that it passes the test? So that would be the probability of A2 given B complement, right? Well, let's write down the definition of this conditional probability. So it's the probability of A2 and not B, and then this is going to be divided by the probability of not B, right? This is by definition. This is by definition right here. This is by definition right here, right? Well, A2 and not B, that is this path. So moving along here and getting to there, right? So the probability of it being a medium-sized car and passing the test or not failing the test, that probability, which goes in the numerator, is your 0.35 times 0.88, right? And again, we just got it by looking at that right, just looking at the right path, right? If you have your tree labeled and if you look at the right path, it is highly unlikely. Now, there's always a chance, but it's highly unlikely that you'll get something incorrect, right? So that's your numerator, and then now the probability of not B, Well, that's 1 minus this, right? Using our complement rule. So it's 1 minus 0.117. So the numerator simplifies to 0.308. The denominator simplifies to 0.883. And then when we divide that, what are we going to get? You guys want to pause the video and do it quickly? We take our quotient. So yeah, we can write it as a proper fraction. It doesn't really come out really nicely. So here it is as a decimal. It is just approximately 0.3488. So just under a 35% chance that given the test is passed or not failed, then the engine is that of a medium-sized vehicle, right? So you kind of have a choice, right? If you are a formulaic, you love formulas, you just like to, I don't even like the phrase plug and jug, but we know what it means. If you're that type of learner or problem solver, then obviously you have your formulas. If you're a little bit more visual and you like to have a picture that holds all the information that you need, then the tree diagram is certainly meant for you. And again, I put it in the analogy is what the Venn diagram did for us when we essentially just had one layer of randomness. The tree diagram does the same when we have two or more layers of randomness, right? So I hope you found that informative, and we'll see you in the next video.